We're going to take a look at graded muscle contractions and the force produced by single muscle fiber. Graded muscle contractions just means that we're able to produce different amounts of force with muscle contractions. So for example, we need a lot less force to pick up a pencil than we would need to pick up a child. So the amount of force generated by a whole muscle contracting is determined by two different things. So this would be important to remember. So it's determined by the force produced by a single muscle cell. And the more myosin heads that bind to the actin, you're going to generate more force. And so this is going to depend on the frequency of stimulation of the muscle cell, the fiber diameter, and the fiber length. And then it also depends on the number of muscle fibers that are contracting, also called recruitment. So in this video, we're going to be looking at the force produced by a single muscle fiber or muscle cell. So let's start with the frequency of stimulation of the muscle fiber. If you increase the frequency of action potentials in the muscle cell, you're going to increase the amount of force produced by the contraction. So we start with a single muscle twitch, which is pictured here in the graph. And then from there, we can increase to trype, and then we go to summation and then to tetanus. So tetanus would give us the maximum amount of force that we could produce. And then a muscle twitch would be the least amount of force we could produce with a single muscle cell that we were looking at. So from a single muscle twitch, we can increase the amount of tension or force being produced by a single muscle cell and go up to trype. If we stimulate the muscle cell to contract, again, right as it relaxes. So we'll stimulate it to contract, and then as soon as it relaxes, we stimulate it to contract again. We get another muscle twitch, and then as soon as it relaxes, we stimulate it to contract again. And you can see that we get this stair-step increase in tension or force, and that is what trype means. It's a German word for stair-step or staircase, and it's just talking about this increase in tension or force that we're producing as we increase the frequency of stimulation of this muscle cell to contract. And there's a couple of ideas why trype happens. One is that maybe not all of the calcium gets pumped back into the sarcoplasmic reticulum. So maybe there's still a little bit out in the sarcoplasm or the cytoplasm, and when we stimulate it to contract right away again, more calcium gets released, gets added to what was left out there. And the more calcium that is out in the sarcoplasm, more of it can bind to troponin. And that means you can move more of the tropomyosin rope out of the way on the actin or the thin filament. And that means that more of the binding sites on the thin filament will be exposed. And then more myosin heads can bind to the thin filament. And then we can get more cross-bridge cycles going, and we can shorten the sarcomere more, and we can generate more force with our contraction with our muscle cell. Another idea that they think might be happening is with the repeated contractions that are happening, you're using energy or ATP, and that's generating some heat. And so because the muscle cell is warming up with the repeated contractions, the ATPase enzyme that's on the myosin head actually works faster at a little bit higher temperature. So it's able to do that little cross-bridge cycle at a faster speed. And so you can actually shorten the sarcomere faster. And so that'll create more tension or force as well. So couple ideas. They're not sure exactly which one's happening, or maybe both. But that's the idea behind treppe. So you get this stair-step increase in tension as you increase the frequency of stimulation of the muscle cell. You're going to stimulate it to contract as soon as it relaxes again, and you increase your tension up to this plateau there. So that's treppe. And this is kind of the idea behind warming up before a race. All right, the next thing we get into is summation, and this is when you stimulate the muscle cell to contract at an even higher frequency. And what happens is that you start adding the muscle twitches together. So we get summation of the muscle twitches. So remember we talked about before, like in our neurons, we were able to sum and add together the graded potentials. This is kind of the same ideas where we're able to add the muscle twitches together. So the reason that we're able to do this is because the action potentials occur much faster than the muscle twitch does. And the action potentials have a very short refractory period in the muscle cell. And so if we're able to stimulate the muscle fiber to contract again before it's completely relaxed, you still have calcium out there in the sarcoplasm. And so if you stimulate it to contract again, you're going to release more calcium from the sarcoplasmic reticulum. You're going to add it to what's already out there. It'll bind to more troponin. You'll move more tropomyosin rope out of the way. You can have more of the myosin heads bind to the thin filaments and form more of those cross bridges and do more cross-bridge cycling and shorten the sarcomere even more, and that'll increase the force of the contraction. So let's just take a look at a picture of summation. Oh, before we do that, here's just showing you how short the action potentials are in the skeletal muscle cells. So here's how long the action potential lasts. So very, very short. And then here's the muscle twitch in the skeletal muscle cell. So that's lasting a lot longer than the action potential does. So you could have lots of action potentials here before the muscle twitch is even done. All right, so now let's take a look at adding our muscle twitches together. So we'll start with just a single muscle twitch. And then over here, if we stimulate our muscle to contract, here's a muscle twitch here. And then if we stimulate our muscle to contract again before we've completely relaxed, our next muscle twitch will add to what's left of the first muscle twitch. And so you can see that we can increase the tension that we produce, or the force of contraction. And then if we stimulate our muscle to contract before this one relaxes, we can add our next twitch to what's left of this previous twitch, and we can get even more tension. So that's what summation is. And then if we increase the frequency of stimulation of our muscle cell even more, and we don't let it relax very much at all, we can get what's called incomplete tetanus. So tetanus just means rigid. And so we're letting our muscle just relax just a little bit, and we get pretty high tension or force being produced. But the maximum amount of force that you can generate with the muscle cell would be called complete tetanus. So this is where you're going to stimulate the muscle cell to contract so fast that you don't let it relax at all. And so you're just going to add all those muscle twitches together, and notice you're not relaxing at all. And so this is going to generate the maximum amount of tension or force that that muscle cell can produce. So that's complete tetanus. And so tetanus just meaning rigid. You're not going to let that muscle cell relax at all. So that would be complete tetanus. An example there might be, you could experience complete tetanus, like maybe you're lifting something really heavy, or you can even experience that like when you're crouching down. You can see complete tetanus in some of your muscles when you're doing that as well. Okay, another thing that can affect how much force an individual muscle cell can produce is the diameter of that muscle fiber. So the larger the diameter of the muscle fiber, the more force it can produce. So if you have a larger diameter muscle fiber, the more actin and myosin that is packed in there. So let's say that we're looking at a muscle cell here, and we're looking at a cross section, and we've got two muscle cells here, and one's a larger diameter than the other one. The larger diameter one, you can pack in a lot more actin and myosin in here. Okay, and you're going to be able to generate a lot more force than if you had a much smaller diameter muscle fiber. You don't have as much actin and myosin. So like this guy over here on the right, which obviously is a doctored picture, nobody has muscles that big, but I just thought it was kind of funny. This guy would be able to lift a lot more weight than I would, because my muscle fibers are pretty skinny. I'm pretty wimpy. I can't lift very heavy weights, but this guy could lift a lot more weight than I could because his muscle fiber diameter would be a lot bigger than mine would be. Okay, and then the last thing that can affect how much force an individual muscle cell can produce would be the length of the muscle fiber. So our muscle cells are actually set at just the right length to generate the maximum amount of force when they contract. Okay, so this graph is just showing you that the maximum amount of tension or force that you can produce will be up here at the top. Okay, when your sarcomeres are this length, and that's where our muscles are set. Okay, so they are just naturally made that way. But if you were to take a muscle cell out of your body and put it in the lab, and if you stretched out that muscle cell and then stimulated it to contract, it would not be able to produce as much force, because if you stretched it out and stretched those sarcomeres out, it would be hard for the myosin heads to grab on to the thin filaments if those sarcomeres are all stretched out. And so you wouldn't be able to produce much force at all if the sarcomeres are all stretched out. And then also if you took that muscle cell and you were in the lab with it, and it's outside the body, and what if you smushed it up and scrunched it up and then stimulated it to contract? Well, again, you're not going to generate much force, because if you've scrunched up that sarcomere and the Z lines are already hitting the ends of the myosin or the thick filaments, you really can't shorten that sarcomere and generate force. So if they're already scrunched up, you're not going to generate much force either. Okay, so this is called the length tension curve. But luckily we don't have to worry about that, because the muscles just naturally in our body are already set at this optimum length for the sarcomeres, and so we're going to generate the maximum amount of force. So that's already automatically set, so we don't have to worry about that. Okay, so just remember 3 things that are going to affect the amount of force produced by a single muscle cell. Okay, would be the frequency of stimulation. So the faster you stimulate it, you can add the muscle twitches together, and you can go all the way up to tetanus, and that will give you your maximum tension. We also have the muscle fiber diameter. And so the larger the diameter, like that big muscly guy, the more force you can generate, more weight you can lift versus a smaller diameter muscle fiber. And then also the fiber length. So you don't want your muscle fiber to be too stretched out, and you don't want it scrunched up. You want it to be just right, just the optimum length, which in our body is just naturally at the optimum length, so we don't have to worry about it.